Assalamu alaikum and good morning. Today's webinar themed Engineering for Sustainability, Water and Energy in the Tropics is jointly organized by the Mahathir Science Award Foundation and Academy of Sciences Malaysia. The Academy of Sciences Malaysia is an independent organization representing the scientific minds of Malaysia. It carries out strategic studies that are independent, evidence-based, reliable, and timely for the benefit of all. This year, ASM will be celebrating its 25th anniversary. The Mahathir Science Award Foundation seeks to encourage excellence in tropical scientific research that brings direct benefit to countries in the tropics and the global community at large. Annually, we give out the Mahathir Science Award in recognition of the best scientific contributions and innovations to solving problems of the tropics in 4 different categories, namely tropical medicine, tropical natural resources, tropical agriculture, and tropical engineering and architecture. Currently, the call for nominations are open for the tropical engineering, architecture, and agriculture categories. Do visit our website to learn more about nominating. Today's webinar will focus on how we can utilize the abundant sources of water and energy in the tropics. We have some excellent experts that will share their knowledge with all the audience today, and we hope that all of you will come out of the webinar having learned a few things. Now, without further ado, I'd like to invite academician Dr. Mazlan Othman, chair of our upcoming conference on tropical sciences, TropSci 2021, to give her welcome remarks.
Assalamu alaikum wa rahmatullahi wa barakatuh. Good morning, everyone. Welcome to the series of webinars on the theme of The Future Belongs to the Tropics. Allow me in a few minutes to give you some insight on why we think that the future belongs to the tropics. Now, the tropics as a region accounts for 40% of the world's total surface area, hosts nearly 95% of the world's mangroves, hosts approximately 80% of the world's biodiversity. 54% of the world's renewable water resources are in the tropics, and 82% of the world's living languages are spoken in the tropics. By 2050, the region will host more than half of the world's population and 2/3 of its children. But at the same time, 85% of the poorest people in the world live in the tropics. So while tropical nations have made significant progress, they face a variety of challenges that demand focused attention across a range of development indicators and data in order to realize their sustainable development goals. To bring about this awareness, the Academy of Sciences Malaysia, as you have heard, established the Mahathir Science Award that endows $100,000 to scientists who make significant contributions to tropical sciences. To support this prize, we are organizing the International Conference on Tropical Sciences, their contributions to sustainability, or TropSci, in the second half of 2021. Many activities will be held to build awareness of the goals of TropSci 2021 to attract participation among policymakers, implementers, both in the private and public sectors, and researchers. Thus far, we have covered the topics of mangroves and youth in the tropics. In October, we cover the topics of coffee and cities, and in December, mountains. Today, we present to you a webinar on engineering for sustainability with the theme water and energy in the tropics. Now, although the tropics has 54% of the world's renewable resources, almost half of its population is considered vulnerable to water stress. It is well noted that the existence of rivers and rain-fed arable land in tropical regions provide the conditions for most renewable energy sectors to flourish. And yet, over 79% of the people in the tropics had access to electricity in 2017. Clearly, energy resources in the tropics need to be further exploited to ensure equitable standards of living for all. With that in mind, today's webinar aims to address these issues by exploring how energy and water in the tropics can be sustainably provided and managed. Ladies and gentlemen, I hope today's webinar will serve as an inspiration as well as a rallying call to those who reside in the tropics, ourselves, on the untapped potential of the tropics and the benefits that its water and energy sources can provide to the people who live there. Thank you and enjoy your deliberations.
Okay, Assalamualaikum and good morning. So we are very fortunate here. Myself, Professor IR Dr. Nur Aisyah Saidina Amin from University Technology Malaysia, and Professor Chong Kok Kiong from
I'm Professor Chong Kok Kiong from University Tunku Abdul Rahman.
We will be the moderators for today's session. The first session, the topic will be energy for the tropics. And this topic will be presented by Encik Samsul Baha Muhammad Noor, who is the CEO of Malaysian Green Technology. So he will be presenting the talk, which was prepared by Dato Bakar and also Professor Dato Kamar Zaman. Okay, so without further ado, I will then think we can start the session, but before that, we can read the background of the speakers. Okay, so for the first speaker, we have here Professor Datuk Dr. Abu Bakar Jaafar. He is the chairman of Malaysian Green Technology and Climate Change Center. Currently, he is also the director of UTM Ocean Thermal Energy Center and professor at Perdana Center, UTM. Razak Faculty of Technology and Informatics since 2013. He has served the Malaysian government in various capacities since 1973, including being the DG of Department of Environment from 1990 to 1995. After his optional retirement, he continued to serve the Malaysian government as the elected member of the UNCLOS Commission of the limits of the continental shelf from 1997 to 2012 at the United Nations headquarters in New York. Okay, so the other person who prepared the presentation was Professor Datuk Dr. Kamar Zaman Sopian. He is presently Professor in Renewable Energy and Director of the Solar Energy Research Institute at UKM. His expertise is in advanced solar photovoltaic and thermal systems and was included on Clarivate's 2019 highly cited researchers list. He has won international awards for his contributions to renewable energy, including the Islamic Development Bank S&T Prize in 2013, World Renewable Energy Network Pioneer Award 2012, 5 ASEAN Energy Awards, World Green Technology Grant Award 2015, and the World Society of Sustainable Energy Technologies Innovation Award for Renewable Energy System in 2019.
Encik Samsul take on behalf of Abdul Bakar.
Okay. He is the current vice chairman of the World Renewable Energy Network. Okay, so maybe a little bit about ourselves, the moderators. So as mentioned, I'm Professor Nur Aisyah. I'm the head of Chemical Reaction Engineering Group at the School of Chemical and Energy Engineering, Faculty of Engineering, University Technology Malaysia. So my field of expertise is in catalytic reaction engineering and modeling of chemical reaction systems involving gas and biomass. So Professor Dr. Chok Kok Kiong, who is with me here. He is a full professor at University Tunku Abdul Rahman, specializing in solar energy and a chartered engineer with Engineering Council UK. So he has received recognition from numerous awards and fellowships such as the Top Research Scientist Malaysia, Malaysia Tourist Science Foundation, and also the JCI 10 Young Outstanding Malaysian. Okay, and he is also an associate editor of Frontiers in Energy Research. So the speaker today is Encik Samsul Bahar Muhammad Noor, who is the CEO of Malaysian Green Technology Corporation. So without further ado, we will invite Encik Samsul Bahar to give the first talk this morning.
Thank you very much. Hi, I'm Shamsul. I'm filling in for Professor Dato Engineer Dr. Abu Bakar Jaafar. He apologized for not being able to attend and present the topic himself. I will be presenting the first half of the presentation, and Professor Dato Dr. Kamaruzzaman Sopyan shall present the concluding part. I will share the screen, just a moment. Okay, can all view the slides? Okay. The topic is energy of the tropics towards hydrogen economy and sustainability. For clarity to all participants, we have divided the presentation to 5 main parts. After the brief introduction, we will discuss on the forms and sources of energy in the tropics, ocean thermal energy, hydrogen, and the way forward for Malaysia and other tropical countries. Now, yes, okay. The Earth is made up of 70% of ocean and only 30% of land. So we have a vast area of water that covers the Earth. And if you look at the form of energy, 70% coming from heat, either by conduction, convection, or radiation. And only 30% of the other forms of energy, potential energy, kinetic energy, biological, chemical, and geological. According to Sadi Carnot, a French physicist who were often described as the father of thermodynamics, the mechanical energy can be extracted from the flow of heat energy between a hot and a cooler region. Now, within the tropics that we are living in, the sea water surface temperature is more than 24% degrees. And the average ocean temperature differences ranges between a differential of 20 degrees Celsius. And in a study made by an American physicist, Clarence Zanet, there is a huge potential for ocean thermal energy conversion, or OTEC, in the tropics. In brief, OTEC uses the ocean thermal gradient between cooler, deep, and warm surface seawater to run a heat engine and produce electricity. OTEC has a very high capacity factor of 95%, and this is very important as opposed to other forms of energy. A working fluid, usually ammonia, is being heated by the warm seawater and converted into gas. Ammonia has a low boiling temperature. When turned into gas, move the vapor into pressurized shafts and are then used to drive turbines to produce electricity. The much cooler deep sea water will then use to cool down the ammonia vapor back into liquid, and the process continues. So this is the very much the fundamental of OTEC. Now, as opposed to wind and wave power, they have more potential in the temperate region. But for our own region, OTEC is the one that we are actually having the largest potential. So OTEC would be best to be implemented within the tropics. According to the Academy of Science Malaysia and Technology Foresight Malaysia 2050 report published in 2017, OTEC is listed as the 21 impactful emerging technologies to elevate Malaysia's well-being, wealth creation, and governance for sustainability to reduce Malaysia's carbon footprint drastically. There are so many studies and IP patent made on hydrogen and OTEC, mainly US patent and WIPO, European Patent Office. However, Malaysia have none. However, what we are looking at now, UTM has come up with a study of nanofluid. Now, nanofluid is the working fluid that I mentioned earlier that can replace ammonia, and it has a very, I would say, similar properties as ammonia that can be heated up with just using warm water. And comparatively, tidal energy, if you look at this particular graph, it shows that tidal energy and wave energy and salinity gradient has a higher electrical output versus OTEC. However, what we're looking at is the OTEC has the highest capacity factor of 95% as opposed to the rest. Capacity factor is the number of hours that OTEC can utilize, which actually can be run for 24 hours, 24/7, as opposed to solar PV, which only have a certain number hours whereby the sunlight will actually radiate the earth, which is only about 4 to 5 hours per day. So as opposed to the rest of the other possible energy, OTEC has a better potential. Now, and also OTEC meets all SDG 17 goals. And studies have shown that in Malaysia, particularly in Sabah, we have a huge potential of having an OTEC operation. The area in the coast of Sabah has the potential to produce 26,000 of megawatt of electricity. And the next slide, this is on hydrogen. And you can see that there are abundant of hydrogen on Earth in various forms. And it is the most dominant energy carrier in the 21st century. With the declining source of coal and oil, hydrogen and alcohol is the future. And hydrogen from natural gas, which is blue hydrogen, and from water, which is green hydrogen, has been developed. And what we're looking at is the production to produce hydrogen in the much cheaper, much feasible operation. And a lot of work has been done, and we believe that hydrogen has a very huge potential that can replace the other form of energy. In a survey conducted by Professor Datuk Bakar Jaafar in 2014, hydrogen fuel cell gets the most votes as the type of energy that will dominate the world. And the way forward for Malaysia and other tropical countries, hydrogen must be the focus. Solid state hydrogen is the best option for logistics and mobility. It can be transported at a low cost and it is very safe. There are so many methods to produce hydrogen. The lowest hanging fruit would be to convert hydrogen from the excess pressure in the water distribution network. Then you can also produce hydrogen via solar PV, biomass and waste to energy, and obviously OTEC. All of these forms have hydrocarbon, which the hydrogen can be separated and to actually produce hydrogen and be kept in either solid state form or liquid form. In my last slide, before I hand over to Professor Dr. Kamruzaman, let us look at the sustainability index. Malaysia is low in renewable energy. If we could increase RE, we could reduce the greenhouse gases and more energy saving and energy usage can be produced out of it. I hope this will clarify the slides and presentation of OTEC and also hydrogen moving forward. I pass it over now to Dr. Kamruzaman.
Assalamualaikum warahmatullah. Thank you very much. The presentation basically will cover the role of basically renewable and carbon reduction. I would like to basically complement the previous presentation and will present basically two parts. Number one is actually I would like to basically present the outcome of our carbon-free roadmap that 2050, a roadmap that was actually developed by a team, basically from a team from the Academy of Science. Is as a result of a workshop that was conducted by the Academy of Science and a team of professional and academics from Malaysia. And also, I would like to also present the innovation that is required basically to achieve this roadmap. And this includes system operations, enabling infrastructure, what sort of business model, as well as the market regulation. Innovation in those areas are very pertinent basically to achieve the roadmap. Now, I would like also to invite all of you to basically download this particular document from the website, which the address I have shown in the slides. The title of the document is Carbon-Free Energy Roadmap for Malaysia. And basically, the scope of the renewable energy covered for these are bioenergy, geothermal, hydrogen, nuclear, OTEC, solar and tidal wave, tidal current, wind, and as well as hydrogen. Hydrogen generation from new renewables are considered to be energy carriers and has been proposed, and hence fuel cell technology has also been included. This particular roadmap basically also have the assumption that there is 10% energy reduction due to innovation in energy efficiency. So the two scenarios are developed for this roadmap. Scenario number one is carbon-free energy mix in electricity generation. And scenario number two is net carbon emission, electricity generation, net zero carbon emission, electricity generation. In scenario number one, zero fossil fuel consumption in electricity consumption generation by 2050 has been developed. And in scenario number two, the total carbon emission avoidance from carbon-free energy resources basically will offset the emission from the fossil fuel combustion by 2050. Now, in the first scenario, is actually scenario number 1, carbon-free energy mix in electricity generation. It means that it's zero fossil fuel consumption by 2050. Here are some of the results. The workshop basically gathered stakeholders from the professional and academics, as well as from the banks, from the financial institution and so forth. So we come up with this particular technology, basically these results, and we use scenario analysis, backcasting analysis, basically to come up with this particular results. For scenario number 1, as you can see, is zero use of fossil fuel by the year 2050. And you can see the distribution of the use of the various technologies, for example, OTEC, fuel cell, wind energy, biomass, PV, tidal wave, nuclear hydropower, geothermal, and the fossil fuel, of course, is depicted by the green color here. For electricity generation by energy in terms of gigawatt hour, because you know that in some of the energy resource is actually intermittent. So therefore, they don't give you 24 hours in terms of power. So you basically can see here the energy generation in terms of electricity generation in gigawatt hour. And the installed capacity for hydrogen generation is shown here. In 2050, basically, most of the hydrogen generation is from OTEC, followed by solar, wind energy, wave, and of course, nuclear. In terms of total capacity by energy resource, this particular diagram shows you in terms of megawatt, the total capacity of total installed capacity. Now, in terms of carbon emission, you can see that between 2012, the baseline studies, until the year 2050, this is the carbon emission reduction, basically for scenario number 1. For scenario number 2, we have net zero carbon emission in electricity generation. It means that the net zero carbon emission by 2050. Here, again, the definition is that the total carbon dioxide emission and avoidance for carbon-free sources will offset the emission from the fossil fuel combustion by 2050. Again, here we show you the energy resource by electricity mix. At this time, you can see that the fossil fuel is still used, but this is actually offset by the use of renewable energy. It means that the net zero carbon emission, the carbon emission is net zero by 2050. Here shows you again all the technology available, and this is the contribution of the renewable energy as opposed to the gradual lowering of the usage of fossil fuel. In terms of gigawatt hour, in terms of energy resource, it is shown in this diagram. Again, you can see here that in this particular scenario, here are the potential renewable energy usage for Malaysia. And for the installed hydrogen capacity generation in terms of megawatt, is shown in this particular diagram. Now, in terms of total capacity of energy resource, again, we can see there is an increase in the use of it. And finally, I would like to show you this in terms of year 2015, the use of this, and then followed by in 2025, 2030, 2035, 2040, and finally in the year 2050. Here are the energy resource for scenario number 2, and the total capacity of the energy resource is about 86,000 megawatt, 86,000 gigawatt. In terms of scenario number 2 for the carbon emission is shown in this diagram. So it will be net zero in the year 2050. Now, in the second part of the presentation, I will give you some example, some innovation that is basically required basically to enable us to basically go forward in future. Some of the innovation are already here, but here are some of my suggestions and some of the suggestions from Prof. Dato' Bakar. Okay, if we look at the innovation in terms of innovation in power trends, you can see that in terms innovation in future power systems include digitization, energy IR 4.0, big data, and so forth. And then there is a way forward basically to look into decentralization, and of course, a flexible system. And finally, you have to look into the electricity and the end use. And in terms of flexible system, it means that it accommodates the largest possible renewable energy of share between renewable energy sources. And in terms of the way forward for this is actually to establish a sort of net neutral renewable energy community. And in the net renewable energy community is that basically a community, a facility, or a center is considered to be net neutral if the net energy import is not required from outside. It is generated within itself. So this is called the concept of net neutrality. And this is the framework formulation to achieve the net neutrality. And this is part of the systems operation innovation that is required basically in order to go forward for the hydrogen economy. A small example here is a project that we did in a small place, in a small Orang Asli village in Tioman. Sorry, in Tasik Chini, sorry, whereby the community itself basically generate its own energy. The concept of low energy house and ultra low energy house, BEI of maybe 50 and below, would be the way forward basically for buildings. The use of all energy efficiency means and also renewable energy. We have one particular show house basically that has all this concept. The next, another enabling structure is that the use of, again, artificial intelligence, internets of things or internets of everything. So these are some of the examples that basically can, some of the innovation that is required basically. And for example, in future, for example, we have virtual energy audits. You don't have to physically go to the buildings, but you do it virtually. Another part of it is basically the cost reduction of many energy devices. An example of this is actually the PV panel. The PV panel now, the cost is about 40 cents per watt. Therefore, it means that to go more competitive, it should go beyond that, below that 40 cents per watt, 40 USD per watt. And of course, there are some process in making the solar panel, which is basically toxic. Some of the these are the conventional process, but there are processes which involve a lot of acid, a lot of flammable material. And in the future process will not include this. So therefore, if you look at this process are required basically to achieve some properties for the solar panel. But the future process will basically dry process, and the process whereby the elimination of the usage of many of the combustible material that is basically used in the production of solar cell. And of course, the future solar cell would be tandem. It will include multiple layers so that it can go beyond the 40% efficiency rather than the present 20% for the single junction. In addition to that, some sort of innovation should be needed. For example, the use of photovoltaic thermal collectors, whereby it produces simultaneously the production of heat and electricity. This is an example of it. You can see that your panel actually, when you put it on top of your roof, basically it is about 50 degrees C, but you can use it in a specifically designed absorber. You can basically pick up the heat. Solar thermal, yes, something is underrated. It should be also reused. Yeah, for example, this is an example of a solar thermal system that was used at the hospital, University Kebangsaan Malaysia. And coming back to the hydrogen economy, the hydrogen economy basically treats hydrogen as a carrier, not as an energy resource. It's a carrier. So it is a different paradigm. Therefore, you can see that all the primary energy resources basically is used to generate hydrogen. And hydrogen is then used in all the sectors. An example of it, if you look at the normal conventional system, you can see the electricity generation efficiency of a power station for a coal power station is about 38%. And if you take into consideration where it comes from and so forth, it's about 38%. But in terms of hydrogen, you can see that it becomes 40% because it is much cleaner and a much more energy efficient and also a much environment-friendly process. We have basically installed one system in our campus in the early 2000s. It's a hydrogen eco-house. It's a grid-connected PV system that produces hydrogen. And also it's grid-connected. And this is the house, the eco-house. And also with regards to the business model that we like to introduce is actually the business model that has to do with the blockchain. For example, the new Muslim, the excess electricity can be also what we call imported and exported using the blockchain based network security systems. And also these are the normal feed-in tariff. We are not using this anymore because this is a subsidized program, but it's good for a start. And then we go into the net metering. So we should have, in terms of market regulation, we should go into more beyond that, perhaps, other than the net metering and, and probably sharing of roofs. But and I think this program basically has been introduced by the ministry. And finally, to conclude, I would like to basically take you into this particular diagram here, whereby between the year 2020, 2030, and 2050, basically what is needed, and the investment needed is actually a lot for this. It is divided into three during the first decade, 2020 to 2030, and we should go more on energy efficiency, on the concept of this net neutral, low energy buildings and so forth, smart grid, and try to decentralize the system. And this so-called is evolutionary. This is what we are supposed to do, but we have to accelerate it. And most of our products should be more environment friendly because, and of course, we should go for the concept of small is profitable. Yeah? And then followed by a destructive way in the 2030 to 2040s, yeah, in terms of the use of renewable and green energy, and also transition towards the green energy and the usage of decentralized system, for example, or tidal wave offshore wind and so forth. And finally, in the 2050 and beyond, we should go and look into, the energy supply stability and the hydrogen economy and the use of advanced renewable energy system, yeah, towards the future, towards the 2050s and beyond. With that, I would like to thank you. And I will now back to the two commentators. Thank you. The two facilitators, sorry.
Thank you, Datuk Kamaruzzaman, and also thank you to, I think, the speaker from the Malaysian Green Technology. Okay, so now we are into the question and answer session. So we have one question here. So I'll be read it, okay? question is, what are the challenges to implementing OTEC in Malaysia? So I think
The question.
the CEO.
Yeah, I would like to answer that. The buy-ins. Even though the technology is there, however, the financing part of it is quite huge. We're looking at a huge investment, and only the government or collaboration with the private sector can pick it up. Then we can actually materialize this. But having said that, if you look at the capacity factor that I've presented earlier, it's 95%. The ROI will be much more feasible because you're looking at a certain number of years that you can actually get back your returns. But the only thing is that the investment is huge, and we call upon the energy sector oil and gas, to actually embark into this particular project, because as you see that currently we are at the peak oil, whereby there'll be a scarce of supply of fossil fuel, namely petroleum. So if we are able to actually move into OTEC as fast as we can make the difference. By the time there is the problem in supplying of petroleum, we can actually have another sort of form of energy that we can harvest, that can supply to, in this context for Malaysia, energy supply. So again, the question is, the answer is the financial part of it is the main concern. Thank you.
So I have question to the Professor Kamaruzaman. Wow, it's interesting to have the roadmap up to 2050. We would like to know, I think most of audience also would like to know, what is the challenges to achieve the zero carbon emission in this 2050 roadmap?
When we were tasked to do the roadmap, I basically I was the chairman of that particular task, and to achieve that, we would like once and for all basically to use quantitative data to basically come up with something that basically in the year 2050 what will happen. For example, for the solar part, there are various restrictions. Number one, in terms of the capacity factor, because solar only produce during about 5 hours a day, or less than 5 hours a day for Malaysia. Therefore, the capacity factor, as opposed to OTEC, OTEC is the capacity of 95%, because it's almost, because the temperature difference of the ocean is almost constant. So therefore, it is able basically to generate that with that capacity factor. Even wind is better than solar, because it actually, the wind blows day and night. So therefore, when we come up with this, we want to have a quantitative figure of how much contribution of each of these various energy resources that can contribute towards the carbon reduction. The restriction, for example, for solar, for instance, is the number of land, the number of rooftop. You're not going to make an umbrella for whole Malaysia, right? So therefore, there is a restriction in terms of that. So that's why we come up with it. Now, secondly, having said that, the next issue, basically to come up with that, because we wish for a zero carbon emission by the 2050. So the step towards it is a transitional step. It cannot be done overnight. It has to have a lot of innovation. It has to have a lot of investment. But it is worth, because it creates jobs. It creates much more environment friendly problem. This particular challenges has to be dealt with. And of course, there are various strategies that you can basically go into, basically to come up with a what do you call it, an acceptable framework for that. Number one, there should be a good government policy for that. Number two, the financial mechanism has to be there. Number three, what do you call it, the funding, the university industrial collaboration should be there. And of course, finally, awareness, education. So here are the challenges that you can see, for us to go into the future and to have this carbon-free future. Okay.
I think this will be the last question. Okay, so probably this question I will direct it to Cik Samsul. So Cik Samsul, this question says, assuming there are only limited resources to implement green technology, which are the best areas to focus our resources on?
Okay, I think the answer will be straightforward. It's hydrogen. We have abundant of amount of hydrogen available, even though it's in different forms. But harnessing hydrogen is the simplest way forward. You look at what Sarawak is doing currently. They are producing hydrogen from hydro, and even though the investment is quite high at the moment, but you look at the economy of scale. So what we are looking at is to have various forms of production. You can produce it from using solar. You can produce it from waste to energy, because hydrocarbon does have hydrogen within it. And also the other forms is to produce it via the pressure from the water tank. So there's a lot of work have been done, and I understand that universities are very much into the advancement of the production of hydrogen. The only thing that hinders it is how to actually collaborate and bring all together. Just to share, next month we'll be having a workshop that will call in most of the universities, the academia, the industry players, the government stakeholders, to discuss on way forward for hydrogen economy. As in the slides shared and also mentioned by Datuk Kamaruzaman, the hydrogen economy is the main focus that Malaysia should be embarking upon. This is the simplest form of energy that you can get. Even though it's not energy, it's actually it's a carrier, but you can actually utilize it in mobility, in heating up homes, almost composed of a lot of ranges spectrum of application. So this is the main form of energy that we encourage Malaysia to actually take it forward. Thank you.
Thank you. Thank you both speakers, Mr. Samsul Bahar and Professor Datuk Kamaruzaman. So now we will go to the second session. Okay, Professor Chong will take over.
Yeah. So the second session we have is topics on the water resource assessment and management in the tropics. Our speaker is Dato' I.R. Lim Chow Hock, Fellow of Academy of Sciences. First of all, I would like to introduce a little bit about the profile of Dato' Lim. Dato' Lim is the past president of Institute of Engineers Malaysia. Currently is the chairman of Malaysia Capacity Development Network for Water Resource Management. Before retiring in 2014, he served as the Department of Irrigation Drainage Malaysia for 36 years. He has extensive experience in the field of irrigation, agricultural drainage, flood mitigation, urban stormwaters management, and river engineering, coastal zone management, hydrology, and water resource management. So he is has a very is a very experienced person in the water resource. So we would like to have Datuk Lim for the session. Thank you.
Thank you very much, Professor Chong, and also Professor Aisha for the kind introductions. And a very good morning to each and every one of you. I'm asked to speak on water resources assessment and management in the tropics, which I will touch on in general. But there will be most of the informations and recommendations will be based on the Malaysian experiences. I should briefly introduce the tropical regions and its climate, and then touch on the common issues and challenges related to water in the tropics. I will then focus much of my time on water resources assessment, water resources management, and then finally the way forward for sustainability. Right, let me take you to according to the Köppen climate classification. The tropical zone falls between the Tropic of Cancer and the Tropic of Capricorn, which are at the 23.5 degree latitude. The tropical region covers 103 countries, I would say representing about 40% of the area of the planet. And currently, tropical region has about 40% of the world population. And it has been forecast that probably by the year 2030, you will reach 50%. And coincidentally, most of the third world country falls within the tropical region. For your information, countries within the tropical experience wide variations in terms of temperature, relative humidity, rainfall. I would say that all these are very much influenced by other factors as well, such as the topography, the wind, and the oceanic conditions. However, the annual average rainfall within the tropic can vary from 1,005 millimeter to more than 3,000 millimeter. Temperature ranges from about 20 degrees to 32 degrees centigrade. Relative humidity from about probably 60 to 80 degrees, and open water evaporation from about 1,006 to 1,008 millimeter. Let me then touch on the common issues and challenges related to water in the tropics. In terms of population growth, South America, Africa, and Asia will reach 3.5 billion by the year 2025. And out of this, about probably 2.5 billion will be within the tropical region. We all know that urbanization and industrialization trends of most developing countries, certainly I think they're also increasing most of the time, like us in Malaysia, and about 60 to 75% will probably be staying in the urbanized area. Hence, the per capita demand for water will also be increasing. And I must say that apart from this, 45 to 55% of the potable water will be needed again to support the growing industries in the region. And everybody is trying for industrial growth, you see. So hence, the demand for water definitely will be increasing. And it's also envisaged that more water will be needed for irrigation for the purpose of growing the staple food. And this can varies from 30 to 70% of the total water resources available. And I must say, worse still for countries that practice irrigations, especially in the tropic, there's a high wastage of water due to the low irrigation efficiency. And most countries probably is even below 50%. In terms of water resources, rivers pollution is getting worse in most urbanized areas of the developing countries as well. I would say that from the UN report, water management is the crux of the whole issues, where applications and implementations of water resources management remains very low as well. And I must say that in terms of all the figures that actually were experiencing in the tropical regions, there will be even the extreme hydrological events going on even without the impact of climate change, I think there is more severe drought and flood as well. This is the map that shows a freshwater model according to the water gap, which stands for Water Global Assessment and Prognosis. This freshwater model was developed at the University of Kassel and the University of Frankfurt in Germany, and it predicted that freshwater scarcity will even become worse in the future. By now, probably most of you have heard about these 17 global sustainable development goals, and specifically Goal 6 talk about providing clean water and sanitation for all by the year 2030. However, according to the United Nations Water, the world is not on track to meet this target. And having noted the various water issues in the tropical region, I would say that hard question today is there really fresh water crisis in the world, especially in tropic regions? Again, according to a survey by CANET of UNDP, many world organizations believe that water crisis is mainly governance crisis. That's take me, ladies and gentlemen, I would like to move on to the aspect of the water resources assessment. Water resources assessment is actually the determinations of the source, the extent, quantity as well as the quality, and the dependability of water resources for their utilization as well as for control. And in the past, I think this kind of so-called assessment has been loosely termed as a water accounting, water resources audit, etc. But I think more important is currently a comprehensive approach is to carry out what we call a water balance study. There is a balance between the water available and the socio-economic as well as the environmental needs of the nation. And hence, I think for every nation, more so in the developing country, the necessity to develop national or perhaps even regional water management system. Let me just give you an example of Malaysia. I think the Department of Irrigation Drainage Malaysia has been conducting this kind of national water balance study, or NAMOPS as they call it, for many major river basins throughout the country. I'm not going through in details, but just to suffice to say that there are 9 outputs from the study. More importantly, is the outcome. The important outcome, number 1, predicting the possibility of drought 2 months in advance, which I think is very good, and giving 2 weeks advance warning. Number 2, assisting in decision making on the priority of water allocation, obviously under adverse condition. And thirdly, providing the information on the planning and implementation of water-related infrastructure for the needs of the country. So you can see that actually the very important aspect of the NAMOPS system for the developing country here. Before I go further, let me briefly touch on the sources of available water for the countries in the tropic region. I think the dependence on fresh water from reservoirs, rivers, lakes, and ponds, I think this can varies from country to country. It can even from 65 to 97%, as in the case of Malaysia. I think all of us know that 97% of our water comes from the river. As for groundwater, that can vary from 3 to 35%. Recycling of used water, I use the word term wastewater instead of wastewater. It varies from 0 to 40%, as in the case of Singapore. And for small country, I think desalination is their savior. And I think, again, in the case of Singapore, it may go up as high as 25%. Let me then take a quick look at the global water budget. All of us know that 3% is fresh water, and out of this, again, 30% is only accessible. And of this 30%, 60% is within the tropic region. Again, just let me quickly share with you for the case of Malaysia, the water budget. We have as much as 2,940 millimeter of rainfalls. And we say that about 496 billion cubic meter sort of runoff, become a runoff in terms of appearing into the rivers. And this represents about 51% of the rainfall that finally flows into rivers or waterways and finally out to the sea. I just want to stress here that of this amount, 70% flows out to the sea as flood discharge of this amount here. 15% cannot be used all the while because we think this is due to sunlight intrusion, and that will leave about 15% is usable what most hydrologists would term as effective rainfall, or in short, ER. In terms of demand, there was a study carried out under the review of the National Water Resources Study way back in 2010. During that year, we needed just about 20% of this effective rainfall. And again, in 2020, it was estimated that probably this will increase to about 23%. And by the year 2050, it is projected that only 25% of this effective rainfall is needed in terms of total demand. And yet we say that Malaysia we do experience water stress. We always blame that they're not rainfalls with the wrong catchment. But let me tell you this, I think it's simply because water is running out of Malaysia. And I think for a simple reason, many of us have forgotten that flood water is indeed a valuable resources. Again, I just want to touch briefly on the climate change. Many of you have probably heard about climate change and water resources. And I just want to show you this slide here. It captures very nicely, a very comprehensive, in a comprehensive manner, the general impacts of climate change. Obviously, all of us know that there'll be changes in precipitation, and this will definitely lead to increased runoff, hence increased flooding. There will be prolonged drought, resulting in prolonged dry period, prolonged droughts will be occurring. Obviously, climate change, all of us know, lead to sea level rise. Moreover, in tropic, I think there'll be more frequent intense tropical storms as well. But all these increases or decreases actually varies from place to place. Let me share with you some of the studies carried out in Malaysia. I think Narim did a study in 2006, and it was projected that there will be increment of 473 millimeter in terms of average maximum monthly rainfall in the states of Kelantan, Terengganu, and Pahang, whereas there will be a decrement of about 70 mm of average maximum monthly rainfall in Selangor and Johor, probably over the next 40 years. And in terms of flood flow, this may increase. There will be definitely an increase due to flood flow because of the extreme weather pattern, and this may range from 6% to 47%. Whereas the low flow probably will even reduce further, and that can range from 35 even to 93%. Again, in terms of sea level rise, the study says that the sea level probably could be rising, ranging from which part of Malaysia we are in, ranging from about 1 millimeter to 1.3 millimeter per year. Let me now move on to the aspect of water resources management. I think all of us are very clear in terms of what needs to be carried out. But just let me recap that. The guiding tenet or principles of a good water resource management are, number one, there must be safe, adequate, and affordable water, including sanitation for everyone. Certainly, I think there should also be sufficient water to ensure national food security and to promote rural development. Thirdly, there should be enough water to spur and sustain economic growth for a higher income economy. And fourthly, there should be adequate water in terms of protections of the environment, especially to preserve flow regime, biodiversity, cultural heritage, and also not forgetting the necessity of protecting the water hazard, such as floods and droughts as well. I think I need to mention that today, the current global approach towards achieving this principle is none other than adoptions and implementations of the integrated water resources management. We heard of this term, I think, very frequently, IWRM. And I think global water partnerships definition is very clear. If I just read to you again, it is a process that promotes the coordinated development and management of water, land, and greater resources in order to maximize the resultant economic and social welfare in an equitable manner without compromising the sustainability of the vital ecosystem. But I think from a natural viewpoint, an effective implementation of integrated water resources management should be based on the river basin system. We have been promoting this all the while. I think in the DID, I think especially in the most of the authorities and ministry, we feel that I think in terms of effectiveness, the way of implementing IWRM should be based on river basin. And some people might want to call this as an integrated river basin management, or IRBM. I'm not going to go through detail here, just to show you that there are 8 basic components. But what I want to say here is that the need to have a right institution guided by the sound policy and strategy will provide the necessary legal mandate to carry out our enforcement functions in a very effective and efficient manners. And in other words, the most important prerequisite for a good water management is a sound water governance. We need a very good water governance, which consists of the policy, legislation, and institution. And I mentioned a water policy, perhaps a typical water policy in the case of Malaysia, will probably go something like this. The security and sustainability of water resources should make a national priority to ensure adequate and safe water for all through sustainable use, conservation, and effective management of water resources, enabled by a mechanism of shared partnership involving all stakeholders. A very beautiful statement that encompasses everything. And in our case, I think the Malaysian water resource policy touched on 4 core areas, and essentially talk about water resources security, water resources sustainability, the kind of partnerships that we need to actually gather, and lastly, capacity building and awareness. And under each core areas, various strategies and action plan has actually been developed by them both, by the various departments and the ministries. And I just want to touch on one aspect. Among the various strategy action plans, it does mention that we need to engage with relevant stakeholders, including even public participations. But however, I think how are we going to engage with all stakeholders effectively? I think this certainly would depend on the cost that will be incurred, as well as the time that's available to carry out such kind of any kind of studies. And I would say that to a certain extent, a certain amount of compromise may be necessary in some cases. I just want to share again in the case of legislations, in the case of Malaysia, water resources regulations in Malaysia is under the state jurisdiction. I think all of us as Malaysians know about that. However, other water-related federal laws are based on sectoral requirement, very much sectoral in terms of the way that our laws are drafted. Some people say that there are as much as even more than 32 current federal and state legislation. And if you go through most of these, I think most of them are overlapping, conflicting, perhaps even still having gaps as well. I'm not going to go into details of it, but just suffice to say that I think some form of a review of all the necessary laws may be necessary in Malaysia. In terms of institution, water resources planning, implementation, regulation in Malaysia, I mentioned that's very much sectoral driven. There is a water policy, but our water policy is so much being spread among the functions of so many ministries in Malaysia. I believe probably so many developing countries in tropics. Here again, we have no single dedicated department within the ministries to provide a complete scope of technical support on water management, as the case in Malaysia. And sectoral-based agencies and organizations, I think will certainly lead to overlapping of functions, inefficiencies, and to a certain extent, a waste of resources. I want to give an example again in the context of Malaysia here. The DID carry out a lot of what we call the hydrological studies, water balance studies, and even river basin studies. But we have another department known as water supply department. They also carry out a lot of studies, catchment studies, and so on and so forth. And to me, I think there are some duplications to a certain extent. I'd like to then move forward and share with you some of the recommendations, particularly for Malaysia. But I believe that what I mentioned here perhaps also with modifications can be applied to other developing countries within the tropics. First one, there are 6 areas I'd like to touch on. First one will be catching total runoff from the whole catchment. I think, ladies and gentlemen, time has come. We do not have the debt luxury to build dam at the upstream anymore. And I think we need to look right up to the river mouth. And I think coastal reservoir, perhaps we have heard the term coastal reservoir before, is the right answer. Coastal reservoir actually can take various forms. It can take the forms of off-river storage or ORS. It can be in the form of barrage with pumping system. It could be even a reservoir within the whole water body itself, within the coastal zone. Now, of course, I think we all the while we say that we do not encourage this because pollution is an issue. No, I think time has come. We must say that with or without coastal reservoir, we should even consider that we should address the issues of pollution. So I think issue of pollution should not be made as an excuse, rather it should be made a necessity to be addressed. I just want to share with you for your information, there's such an association known as International Association of Coastal Reservoir Research. This was formed way back in 2017, and I think the association has been promoting actively on the concept on the use of coastal reservoirs. And if you look at this slide, I think again, this association strongly feel that by addressing the water problem using coastal reservoir, we are in fact contributing to the progress of all the other SDGs that's been actually been mentioned. Right, the second area I'd like to touch on, I think groundwater, definitely the potential groundwater certainly can be explored further. Many countries, I think, should consider it as a conjunctive use, especially for cities and areas that are experiencing water stress. The third area is water demand, for which I would like to dwell a bit more detail. Currently, I think domestic consumption in most tropical countries is high. In Malaysia, we're talking about 210 liters per capita per day, whereas I think our target should be probably brought down to about 180. And others know that Singapore has done very well. They are among probably the lowest, 150 liters per capita per day. And the effort to have this Save Water campaign, I think it is a constant, continuous effort. Obviously, we need to address the aspect of tariff, and currently our tariff is still very low. I think both steps is necessary to increase it in stages. Another area of concern, I think, is the applications of used water recycling, or some people just use the word wastewater recycling, including rainwater harvesting. And I think the target should be 25% by the year 2030 for industries that consume large amount of water. And I think the best way to do is to mandate this in the necessary legislation. There's also a concern about the high irrigation water duty for paddy growing, especially most of the area in the tropical region that grows rice or paddy. And I think in Malaysia, we are using about 30 cubic per acre. That again is, I think, very high. It should be lowered further down, all right? And I would like to move on then to the aspect of the next area of water delivery, the efficiency of water delivery. Concerted effort, I think, again, need to be carried out by both government and water operator to reduce our non-revenue water. Currently, again, it's 35% in Malaysia. We need perhaps to lower it to 25 by the year 2025, and even much lower by the year 2030. Should probably touch, I think we should be able to touch about close to 15%. Similarly, I think irrigation efficiency need to be increased, and I think with the current figure of 52% in Malaysia, we need to probably increase it to 75% for most now greenery areas by the year 2025. And recycling of water for agriculture also, I think, need to be increased probably. And to do so, I think we also need to not to forget that necessary laws need to be amended to impose heavier penalty for water theft and water polluters as well. Let me move on to the fifth requirements, the recommendations. I think this is probably the most crucial. Adequate funding should be necessary, not just for water-related infrastructure, but I think there should be adequate fund to be set aside to invest on capacity building, strengthen our enforcement system, and perhaps even carry out some necessary public outreach programs. These are the soft exposure that we need to carry out. And where government financial resources is an issue, like in most, I think, developing countries, perhaps there's a need to consider alternative funding mechanism as well, such as the public-private partner arrangement. And lastly, I just like to stress again, I think the need for strengthening the water governance. This is a very common area which I think we need to address within Tropics. There's an urgent need to develop, for those who don't have, perhaps to review the national water policy, incorporating all aspects of water resources and water services. And in the case of Malaysia, I think we have both the federal as well as state government. Perhaps it's necessary to obtain the approval and acceptance of the model water law, such as the proposed National Water Act by all states for purpose of uniformity. And where applicable, I think we need to probably reduce some of the regulations as well, in terms of the permissible effluent discharge, I think time has come for us probably to adopt what we call the total maximum daily load, or the TMDL concept, in order to achieve the acceptable level of the receiving water bodies. Again, this should be applied for both industrial and sewerage effluents. And in the case again, I will say that time has come for us in Malaysia to establish a single national water authority at both perhaps with the federal and concurrently at the state level as well. And many are suggesting even we might probably have to look at what we call the river basin authorities as well. Right, in conclusion, ladies and gentlemen, I just want to mention that water resources definitely need to be managed in an integrated and holistic manner by increasing the concepts and principles of integrated water resource management within the river basin. Certainly, we always say that there's always a need for strong political will and commitment to implement all the national water-related programs and initiatives for the benefits of all. I just want to show you finally the kind of a spiral water resources management implementation roadmap for Malaysia. We have actually been progressing, but I think for every step that we take, it should add on to the foundation that has been laid for the sound and sustainable management of water for the benefits of the nation. With that, ladies and gentlemen, I thank you so much for your attention.
Thank you, Dr. Lim, for the interesting presentation. Due to the time constraint, we actually received many questions, but we only can have one question for this session. The rest we will post it in during the direct session. So the question is how the integrated water management can prevent the recent floods in KL.
Yeah, I think to address the flood issue, certainly I think there are many aspects to look into. And obviously, I think land use is one of the aspects. In terms of the land use, approval for land use, that has to be actually considered. And the other area for KL, where the area has already been very much built up, we need to address and look into the adequacy of the existing drainage system as well. The questions of what kind of design criteria that we need to actually adopt for the design of the drainage system, the flood mitigation system, depend very much on whether you can afford or not. We have been saying that the rainfall exceeded the so-called the design criteria. Then the basic question then to ask is, if we increase our so-called drain sizes, the river sizes, especially we might even need another so-called another tunnel on the side of Gombak and the Sentul areas and the Batu areas. That is a question of whether we can afford for another additional cost in terms of the infrastructure to be built. So I think all these factors need to be considered. In terms of public, I think in terms of government regulation, perhaps I think we're talking about all the while that we need to control the so-called peak discharge at the source. And the question is whether we have the additional land to store this water. And that again need to be reviewed again. Right? So I think the various factors need to be considered. Right. Thank you.
Yeah. You want to?
Okay, you can go ahead.
So we thank you for Dato' Lim. So thank you. We will finish this session. We will come to the next session. For the next session, we will have a new topics, which is about the engineering innovation for sustainability in the tropics. Our speaker is Professor Dr. Dominic Fu. He's a founding director for the Center of Excellence for Green Technology, University of Nottingham, Malaysia. For his profile, Professor Fu is a professor of process design and integration at the University of Nottingham, Malaysia. He's the president for the Asia Pacific Confederations of Chemical Engineering and worked on resource conservation and CO2 reductions with more than 50 research scholars across the globe. Professor Fu has 8 books and more than 400 scientific papers. So not to delay, we would like to invite Professor Fu to have his topics, his talks.
Hi, good morning. Let me share my screen. First of all, thanks to Mahadi Science Award Foundation for hosting this webinar series. My talk entitled Engineering Innovation for Sustainability in the Tropics. Right, the main theme for today is water and energy discussion. So I will somehow focus to that two aspects in my talk. First of all, I'm sure many of you seen this Sustainable Development Goals launched by United Nations in, if not mistaken, it's 2015. One of the important goal is this climate action, which is goal 13, right? You may think that climate action is something that is difficult to do, okay? Or you may not even think that this is something relevant to us. Let me show you some photos. Those of you who follow the news will know that California is now experiencing a very drastic wildfire, still ongoing now. They're trying to, doing their best to pull off the fire. If you happen to see this picture of a Golden Gate Bridge of San Francisco, the surrounding area, when you snap a picture, is always in red color because of the dust resulted from the wildfire. And some of you may also remember that the similar incident happens in Australia since last year until early this year, where many animals and human beings are actually suffering from the bushfire. If you think those are far away from us, you probably remember some of the dry season that we had. In this small little town in Perlis, far north of Peninsular Malaysia, they have actually recorded high temperature of 39 Celsius. And this was back in 2017. And they are saying that this is 39 Celsius is not too bad because we are expecting 42 Celsius in 2050, 30 years from now. Those who stay in Selangor will probably experience the water shortage every now and then, of course, for various reasons. Reason one is because of the human being problem. But 2014, we had a very long drought seasons in the year, where the beginning of the year until the end of the year, you can see the picture, February to November, the water level in Selangor River Dam near Kota Kudu Baru is actually lower by half of the normal level. Okay, this problem actually started in 2012, but it fluctuated in 2013, and 2014 was the real big issue where the Selangor experienced a year-long droughts where Shabas have to exercise the water rationing in March and April. That, of course, affect millions of residents and businesses. The same year, some parts of the country experience too much water. Okay, when Selangor have no water, beginning of the year, Kelantan and the other parts of the east coast of Peninsular Malaysia experienced the flood. Okay, one of the probably the most serious floods in our history, and because of all this extreme weather, of course, those who live in Klang Valley will remember this sudden flood 2 weeks ago. You can actually see the Masjid Jamek is on water. Okay, this was not built for mosque on water. Okay, it was because of the sudden flood. Okay, that affect the whole region. So KL has a very serious flood 2 weeks ago, and you can see Masjid Jamek floating on the river. So we need to do something about it. One of these Sustainable Development Goal, okay, this goal 12 is something that we can do about, okay, from engineering perspective, because this has something to do with responsible consumption and production. The goal 12 about responsible consumption and production, I pull a few important ones. You can see that 12.2 by 2030, which is a decade from now, we actually need to achieve sustainable management and efficient use of natural resources, water, fossil fuel, whatever. And by 2020, which is this year, we should actually implement environmental sound management of chemicals and waste. All right, 12.5 by 2030, 10 years from now, we need to significantly reduce waste generation through prevention, reduction, recycling, and reuse. All right, so that are some of the important goals listed in this responsible consumption and production. Okay, from engineering perspective, this is something that we need to do. Okay, and every now and then, industry, if you talk to industry companies, be it chemical production or manufacturing plants or factories, electronic factories, these are common issue that we discuss in the industry. We try to reduce emission, try to reduce operating costs, try to save water, try to minimize wastewater, and improve utility performance and improve profits and efficiency. Now, these are typical problems that we need to face in the industry. Okay, from my discipline, chemical engineering perspective, we always represent our processes in two main domains. One is a mass perspective, the other is energy. I believe this is the same principle that applies for all engineering domain as well. When we talk about mass perspective, we're trying to convert the products, convert the feedstock into products and byproducts. If you get the most efficient conversion, that also means that we will reduce our effluent and spent materials. Okay, so improving the mass efficiency also means we reduce waste at the same time. And on the other hand, we have the energy perspective, where we use heating, cooling, power, and pressure to drive the energy conversion. The utility of the plant or the factory is the energy perspective, where we can make use to do the maximum conversion. So I'm introducing a term to you. If you have heard it for the first time, let me introduce this term called process integration. It's actually a combination of mass and energy integration to make a better use of these resources to perform the maximum efficiency. Excuse me. So the slides show you some of the innovation dedicated by all the researchers in process integration. 1970s was the start of this technique, where some important researchers came up with some method to sort of design and heat exchanger network in order to maximize energy minimize energy usage. I will show a few slides on this later. Late 1980s, we have the mass exchange network synthesis, where solvents and other mass separating agents are minimized. The main philosophy is to minimize waste at the root cause. 1990s, mid-1990s is now already 2.5 decades. We talk about water reduction in the process plant. That's a method that we will discuss in a bit later. We also notice we have a hydrogen integration, trying to recycle hydrogen. Property integration is where we will do the solvent recycling. Energy planning is where we will reduce CO2. Okay, the picture on the right-hand side are the important research scholars in our area of research. Right, the next 5 minutes or so, I will talk a bit on heat recovery system. This was a technique introduced back in 1970s. Okay, when we talk about heat recovery system, we're talking about a process plant which need heating and cooling. Okay, if you look at the picture at the top of the slide, you'll see two reactors. Okay, these are the reactors where produce product from feedstock. Now, there are two feed streams coming to these reactors. Feed 1 and feed 2, both of them need to be heated from lower temperature to higher temperature. So when a stream is to be heated, we call it a cold streams. These are two cold streams need to be heated. After the reactor, the effluent needs to be cooled, okay, to lower temperature before they are sent to downstream operation or storage tank. So these two outlet streams from the reactors are to be cooled from higher temperature to lower temperature, and we term them as hot streams. Hot streams are to be cold. Okay. Now, the table at the bottom indicates the supply and target temperature of these four streams. Of course, when you heat up a stream or you cool down a stream, we will have to indicate the enthalpy given by the delta H. The positive are the streams that need to be heated, okay, from lower temperature to higher temperature. The negative signs for those hot streams to be cooled from higher to lower temperature. Right. What we normally do is to make something what we call heat recovery pinch diagram. In this pinch diagram, we will plot some lines. Okay, by the way, engineering people like to use graphical method. Okay, this is a diagram where we plot temperature versus enthalpy. You can see on the diagram where we have a orange color line. This is actually the hot composite curve. is actually the combination of the two effluent streams, the two hot streams that I have in the plant. I will merge them into this hot composite curve. And basically it's just a cooling profile for this hot composite curve, because the temperature is going to lower down from 250 all the way to 40 Celsius. Okay, this is a heat cooling profile. The stream have to be cooled down, because you notice that the two hot stream we have, stream 2 and stream 4, these are the effluent from the reactor, needs to be cooled from 250 and 200 Celsius to 40 and 80 Celsius respectively. Now, what we next do is to combine the two cold stream. We put the two cold stream together. This two cold stream is going to go from 20 to 230 Celsius. Now, the horizontal distance of these lines actually represent the energy that we need to incur in these streams. For the hot stream, the horizontal distance means energy to be removed from the hot stream. We need to remove the energy to bring the temperature down. For the cold stream, the horizontal distance indicates the energy that needs to be added in order to rise its temperature. So when the two streams are put together in the same diagram, the overlapping region actually tells us how much energy you can remove from the hot to the cold composite curve. Okay, now you can see in the diagram that the overlapping regions labeling down there is QREC, the recovery enthalpy, Q for enthalpy, the energy that we can recover, REC, equivalent to 51.1 megawatt of energy. That means 51.1 megawatt of energy is removed from the hot stream to the cold streams. Okay, so we perform energy recovery using some sort of heat exchanger units. Okay, we'll talk about that later. But on the right-hand side of this composite curve, the extension of the blue line indicates QH min, minimum hot utility needed to provide the heating to rise the temperature to 230 Celsius, because we don't have hot stream over there. Okay, we have to use hot utility. On the left side, there's a QC min. It's a minimum cold utility where 10 megawatt of energy is to be removed from the orange color hot composite curve to the cold utility, maybe cooling water, in order to reduce the energy to drop its temperature to 40 Celsius. So when you have this drawn, we know how much we can recover, we know how much hot and cold utility targets. And the closest region in between the two composite curve is something what we call it pinch. Okay, pinch is actually the closest vertical distance, in which case here is 150 and 140 Celsius. There's a small delta T. Small delta T means a minimum driving force of temperature in order to perform the heat recovery. We need about 10 Celsius minimum, because anything lower than that, your heat exchanger will be very, very large. Okay, once we lay down this, we can actually go on the next stage to design a heat exchanger system. This is a heat recovery system where we will recover the energy from the hot stream to the cold stream. Let me first show you the grid diagram on the top. The two streams coming from the right-hand side to the left, stream 2, stream 4, are the hot stream to be cooled from higher to lower temperature. At the same time, we have two blue lines running from the left to the right at the bottom. These are the cold streams needed to be heated from lower temperature to higher temperature. And we put in some pairs of circles where there are circles, bicircles linked with a vertical line in the middle. These are the heat exchanger that we pair from the hot stream to the cold streams. That will recover energy from the hot stream to the cold stream. And you also notice that I have a small circle with a H, okay, on the most right-hand bottom, which says 7.5. Okay, this is 7.5 megawatt of energy that I need to supply as a form of hot utility. Okay, on the most left, there is a small circle with a C, which is a cooler. I need to remove 10 megawatt of energy from this cooler in order to for the stream to reach 40 Celsius. And 7.5 megawatt of hot utility, 10 megawatt of cold utility is exactly the target that we aim in the earlier pinch diagram. Okay, we identified 7.5 hot utility, 10 megawatt of cold utility, and can be materialized in the design. Okay, in other words, I perform the targeting using pinch diagram. I perform the design using grid diagram. These are two different stages. You can use that as cross-checking to make sure that the target can be achieved using design. And with the target, no one can challenge you. Is this the best I can do? Yes, this is the best you can do, because thermodynamically, you are not allowed to violate the temperature. Okay, so with the grid diagram design, we will convert it back to a process flow diagram, and that actually helps you to identify, where the hot stream are going to recover its energy to the cold streams, and how the whole network whole process will look like, okay? Because we will bring this for the next stage of design. If you want to further optimize, you can look at how utility can be selected in the plant. Usually we talk about high pressure steam, medium pressure steam, low pressure steam. If I have a choice, I will prefer low pressure steam, LP steam, which is the cheaper utility. Okay, high pressure steam can be generated, but you need a more expensive boiler and cost is higher. So for this case, since I need to put in a hot utility of 7.5, you can see it on the circle with a H, 7.5 hot utility targets. In design, we need to optimize it. I will plot another diagram called grand composite curve. That 7.5 hot utility targets can be materialized using a medium pressure steam of 3 megawatts, 4.5 high pressure steam. Okay, of course I can use 7.5 entirely from high pressure steam, but then that also means that I need to buy a much bigger boiler, more expensive. So I would rather prefer to use a medium pressure steam because that can cut down my costs. Right? That is hot utility targets. We add up the two values, 3 plus 4.5 is 7.5, exactly on the target. Below the pinch, okay, we have cooling water that we need to use in order to remove the energy from the streams. Okay, that is equivalent to 10 megawatt of energy. Okay, and cooling water is the system that we need to use in order to remove the energy. Okay, in some cases, you actually can make use of the energy below the pinch to generate power. Okay, that is combined heat and power scheme. Okay, we won't have time to cover that. All right, you can do a search on the book. There are lots of this in the textbook. Now, some statistics shows the energy saving statistics. This is by some Canadian reports. You can see that the saving range from 10 to 35%, depending on the plants that you are working on. Reduced energy also means reduced CO2. It's a direct reduction that helps to promote sustainable development. All right. With that, let me move on to water reduction. We talk about energy. The next important resource that we have is water minimization. Let me first introduce you a very important concept about sink and source. Whenever a unit requires water, we call it a water sink. It demands water for any operation. Can be cooling water tower, can be cooling tower, can be for reactor, can be for washing, can be for scrubbing. A lot of units actually make use of water. We call it a water sink. On the other hand, we have water sources. These are the wastewater that are coming out from any process unit. Some processes have both inlet and outlet of water. It has sink and source. Some processes only have sink, some with only source, okay, depending on what kind of process you talk about. Of course, when you have one wastewater, you know you have one sink, you know where to channel it to. The problem comes when you have a lot of wastewater and a lot of units that require water. So you will have to identify the network that can make use of the wastewater into the units where require water. On the right hand side, you see a spider web that connect between the sources and the sink. Because when you have more than 2 wastewater, channel them to the right units is a tricky thing, okay? Because our objective is to minimize water. If you simply pair it, you can still recycle water, but it's not going to be the maximum extent, okay? When we talk about design, we want to identify a target ahead of design, okay? Let me show you a classical example. This is a production of equinonal trial. In view of time, I won't go through the detail of the operation. Let me just highlight that in the reactor, on the left-hand side, you notice a reactor. This is the place where we will convert the raw material, in this case, propylene. Propylene goes through oxidation process in the presence of ammonia and will produce a product. And this product is called equinonitrile. The reactor outlet stream has 5 kilograms per second of equinonitrile. At the same time, it also produces a lot of water as a byproduct. And we do not want water in our product. So because of the byproduct produced from the reactor, we need to get rid of the water. So in the whole operation, a lot of water are being removed and we send the water to the biotreatment facility, the wastewater treatment plant. Okay. Now, for this particular case, if you want to reduce water, we look at the unit that consume water, where are our water sink. This process has 2 important water consuming units. One is a scrubber. Water is actually used to scrub the equinonitrile product from the off-gas condenser. Okay, another unit is the boiler, where boiler feed water is used. BFW is boiler feed water, is used to produce steam. We need the steam to run the distillation column in a vacuum way. When these two units are consuming water, you add up the two values, you can notice that 6 plus 1.2 is 7.2 kilogram per second. Every second, we use 7.2 kilogram of water in these two units. And a lot of water is produced as wastewater. So if we want to recycle water, the common practice, if you go to the plant, many people actually just tap the final wastewater, sending it back to where the units are required water. Well, you can do so, okay? That can reduce some water, but it's not the best option. Why we say so? I should also remind you that if you want to recycle water, we need to watch out the ammonia content in the wastewater streams. In this case, if you look at the wastewater stream, it has 20 ppm of ammonia content. Okay, if you pull this back to the scrubber or back to the boiler, we need to watch out the impurity content, which is the ammonia. Okay, at the moment it's 20 ppm. If you observe it carefully, this 20 ppm of ammonia actually was contributed by 4 different wastewater streams. It has come from off-gas condenser, decanter, distillation, and Singer injector. All right. These 4 wastewater streams, in the normal plant layout, they basically send to drain come to the buffer tank. If we can segregate the water, do a testing on the quality, you actually notice that some water are actually not that dirty. For instance, the third one from the left, the distillation bottom, that distillation bottom, even though the flow rate is quite small, but it has 0 ppm of ammonia. Why is so clean? Because distillation actually removed the ammonia to the top. So this wastewater have no ammonia. So if you want to recycle, this is the best candidate for recycling. Next is the off-gas condensate, the first on the left. You'll notice that this has 14 ppm. The other 2 wastewater streams are dirtier, 25 ppm for aqueous layer, 34 ppm for condensate. However, when all 4 wastewater mix together, we call it diluted. Okay, the dirty one diluted to be cleaner, the clean one will also become dirtier. Okay, so it becomes 20 ppm because of the mixing of 4 streams. The lesson that we need to learn is do not merge them. Do not mix them unnecessarily. We need to segregate the streams so that it gives you the maximum potential of water recovery. So we usually practice the first philosophy is that we prioritize the use of reuse recycle. You will notice that I do not use membrane, I do not use filter. I basically just channel the wastewater from one unit to the other. We call it reuse. If the water is being recycled recovered in the same unit, we call it recycle. Okay, this is the first priority without using any purification unit, no membrane, no filter, no sand filter, no depth tank, nothing. Okay, why? Because this is the first priority, lowest cost. If you can channel the pipeline directly, you save the cost. Okay, let me show you if I recycle this 4 wastewater back to the 2 units, I will plot something called the sink composite curve. The scrubber and the boiler feed water, I take their values. The table on the top there actually give you the flow rate and the concentration. Second column tell you the flow rate. What I will do is I multiply the flow rate with the concentration. That gives me the impurity ammonia load in the last column. So I take the last column versus the second column. That gives me the sink composite curve that you see in the diagram. There are 2 important messages here. Number 1, total flow rate needed by these 2 units is 7 kilogram per second. Okay, it requires 7 kilogram per second in total. Second important message is maximum ammonia content that it can take is 58 milligram per second, indicated by the vertical distance. The vertical distance 58 means you cannot fit anything higher than 58 milligram per second to these 2 units. Okay, now what I will do next is to put the 4 wastewater streams in the same chart. And you can see that horizontal distance, this is actually very big because the total flow rate of these 4 wastewater streams is 13.1. While the 2 sink only require 7, my total wastewater is 13.1. The total flow rate, horizontal distance of this dotted line is 13.1. However, these wastewater are quite dirty. Okay, if I directly reuse or recycle them, I'm actually feeding 7 kilogram of flow rate, but at 100 milligrams of impurity load. Ammonia content that will be fed to the 2 units is 100 milligrams per second. But the limit told us that I can only feed 58. If I recycle them directly, I'm feeding 100, higher than the limit. It means that the 2 units will have upset. Does it mean that I cannot recycle water? Ponder about it. No, you can still do that. Some people will say, why don't you put a filter, okay? Purify the stream cleaner to recycle. You can do that, but later. Let's do a simplest, cheapest way now. The cheapest and simplest way is to mix some fresh water. If I assume fresh water has zero impurity, I basically will come, because the fresh water comes from pipe, has no ammonia content, obviously it's zero impurity. That will help me to increase the flow rate of that for wastewater. Okay, now I dilute it with fresh water and push the whole line to the right-hand side until it stays below the sink composite curve, because the sink composite curve tells us the limit you can tolerate. The moment I do that, the whole thing will go on the right-hand side and stay below. And you can see that the red line is no longer above the blue line. The blue line is the limit, 58 on the dot at the pinch. Okay, that also means that I need to feed in fresh water of 2.1 kilogram per second. I'm feeding in fresh water, mix it with source 1, which is distillation bottom, and some off-gas condensate water, mix it in order to recycle to the 2 units. So how much I can recycle? The diagram says 4.9. What about this one on the right-hand side? Anything beyond that is wastewater. So I need to still discharge some wastewater. The value is 8.2. However, I know that my recycle rate is 4.9 kilogram per second. I can cut down my fresh water to 2.1. Okay. So this is a target that we have ahead before we actually do the design. Now, if you think the graphical is too troublesome to draw, well, of course, you can use some algebraic technique. Okay, this is a spreadsheet that I did. I wrote a paper for this, and my PhD is basically on this algebraic method. Okay, you can do it using Excel spreadsheet. If you want it to be automated, you can use Excel solver to do it for you. Okay, if you are free, you can download this paper to take a read yourself. It can give you the numerical value on a very exact numerical. Okay, you notice that fresh water is 2.06 on the top of the table. Okay, the graphical say 2.1. More accurately, 2.06. Okay, wastewater is 8.2. FWW is wastewater flow rate, 8.2. If you're more accurate, 8.16. Okay, you can do it in spreadsheet. Okay, I also develop a software and put it up on the web for people to download and use. Okay, free of charge. You can, if you are free, you can just download it and play around with the software. Okay, with that, you can design a network to recycle water. SR1 is source 1. This is a distillation bottom, which I say 0 ppm of ammonia. I can recycle it to one of the units. SK1 is a boiler. If I do not want to recycle water to the boiler, that's fine. I can feed it fresh water. I will recycle the distillation bottom to the SK2, which is a scrubber, because scrubber can take 10 ppm of wastewater. Okay, and then the remaining water will be discharged. Okay, I will recycle 4.1 with 0.8, a total of 4.9 to sink 2 scrubber. The rest will be sent for discharge. And you can see the design like this. I will feed in fresh water to boiler. The remaining fresh water will be sent to the scrubber by mixing the distillation bottom, which is a cleaner's waste. The second cleaner's waste is the off-gas condensate, that is 14 ppm. I will mix partially. Okay, I take a small portion and recycle that. The rest I'll go to wastewater. So the off-gas condensate on the right-hand side and the decanter bottom, a big pot, all of that are discharged as wastewater. Now you notice that fresh water is dropped to 2.1. Earlier on, it was 7.2. You add up the volume needed for scrubber and boiler, 6 plus 1.2 is 7.2, now dropped to 2.1. Wastewater from 13.1 dropped to 8.2, a reduction of 4.9. Why? Because we recycle them. Okay. Now, if you think the recycle and reuse is not achieving whatever you aim for, you want to go more recycling or recovery, okay, that's the next option. Okay, we will implement regeneration, recycle, or reuse. Okay, when we talk about regeneration, you will have to buy some either filter, membrane, adsorption, dissolved air flotation, adsorption unit, ion exchange, whatever you name it. There are tons of technology under the sun. As long as you have money, you can install it. But that means you need to put in some capital costs. Okay, so that's why we say this is a second priority. The first priority is always reuse, recycle. If you think this direct reuse recycle is not achieving what you're aiming for, you want to explore further reduction, yes, we can do so. Let's buy some units to install and then see whether it can help you to recover more water. Conceptually, it's taking the waste from the end of the composite curve, put it through a unit, purify it, reduce the fresh water. Okay, so I'm demonstrating one option here. I'm using a resin to do adsorption, remove the ammonia content from the off-gas condensate, because this is second cleanest waste. Okay, distillation bottom have no ammonia, so I don't need to put anything. So if I put some adsorption resin there, I will be able to absorb that 14 ppm down to 11.6 ppm ammonia, clean enough. You notice this time, every single drop of off-gas condensate can be recycled because I already purified them. That also means that I do not need to feed fresh water to scrubble. However, my boiler still consumes my fresh water. Still fine. I reduced fresh water from 2.1 just now down to 1.2 kilogram per second. Wastewater just now 8.2, now 7.3 kilogram per second. Okay, if you're still not happy, you want to make changes, remove the fresh water needed for boiler, you can do so. You will get rid of that steam jet injector, replace it with a vacuum pump. That will get rid of water usage. Okay, you will be operating a vacuum pump rather than a steam jet injector. However, you probably have to shut down the distillation column or parts of the plant for 2-3 weeks before you can install and restart the whole unit again. Okay, you will have some production loss. Okay, and you have to invest money in a vacuum pump. Okay, this is not an easy task. But then the good news is you cut down fresh water completely, wastewater drop to 5.9. Okay, let me give you a summary of this particular simple exercise or example. Before you implement reuse recycle, we talk about fresh water of 7.2, original base case. Wastewater is 13.1. If you implement direct reuse recycle, it's 2.1, 8.2 for freshwater, wastewater. If you implement regeneration, down to 1.2, 7.3. If you change the process, freshwater completely remove, wastewater is 5.9. Of course, this sounds very, very good. However, please remember that if you have to do regeneration or process changes, you need more money. Okay, that's why I always say the priority is always direct reuse recycle, because cost-wise it's minimal. You can call your workshop people to implement the piping, rechanneling, pumping for you. Some people have some spare pump, you can make use of that. Minimum cost solution. Okay, impact relatively less. If you invest more money to buy a new unit, to let's say membrane or resin or adsorption or distillation, whatever, to regenerate the stream for reuse, you need to put more costs. Of course, you can cut down more flow rate. Okay, you see that regeneration can cut down more. Wastewater also cut down more. However, you need to produce, make up more money. Okay, if you want to make changes, for instance, in this case, you replace with a vacuum pump, you need to shut down the plant. Even cost more because of the production loss. Okay, obviously, we call the low-hanging fruits are the reuse recycle option, where the acceptability is highest, easiest to implement. Okay, and you want to invest more money, acceptability is lower. Okay, you want to shut down the column, acceptability even lower. So that's why the priority is reuse recycle first, then we do regeneration. Process changes the last. Okay, the statistics shows that typical water saving about 25 to 40% for refineries, pulp and paper, chemicals. All these are reported. Okay, now let me conclude my talk. If you forget whatever I talked earlier on, that's fine. The important take-home message is this: this technology address a main philosophy about big picture first. We talk about the details later. If you notice that this exercise will take you maybe 20 minutes or half an hour, that can help you to target the saving that you can achieve. Okay, if the saving is only 5% and you say 5% is nothing, okay, don't waste your time. Do something else more important. Focus your effort in other more important projects. Okay, if the saving is 30%, 40%, which you find it useful and you find it reasonable to move on, we then go on the details to look at what pump should I use, where the piping should be channeled, what pipes should I buy, what sort of unit should I buy, your membrane or distillation or whatever. So those details will come later. The analysis that I'm put forward here is to show you that within 10 minutes, sometimes 20 minutes, you know how bigger saving you can get. If your saving is significant, you move on, or else abandon the project. Okay, if you wish to do some readings, these are some light reading materials. Normally tell my students, if you cannot sleep, these are good materials to help you to sleep. Okay, these are public material you can download from internet. Should acknowledge all my collaborators. They are all these important collaborators all over the world, from US to Europe to Asia to Africa. They have been helping me to develop all these resource conservation tools every now and then. With that, thank you very much for your attention. I hope we do have time for Q&A, or else we will do it later. If you feel free, if you have any questions or info or exchange, feel free to drop me an email. Right, thank you. I'll pass back to the chairperson.
So Yeah, thank you, Professor Fu, for the very detailed and very very good explanation about this engineering design.
Sorry, I
Due
talk
to
too fast because of time constraint. I talk very fast.
Due to the constraint of time, so we can't have a question at this moment. But we will have a dialogue session. During the dialogue session, we still can have a question to Prof. Fu. So thank you. We will end this session. We will come to the next session on the panel discussion. I pass it to Professor Aisa.
Yeah. Okay, so everybody, we have now come to the last session that is on the panel discussion on water and energy for sustainability. So with this, in this session, so we will have 4 speakers, who are IR Lachlan Gulabrai. So he's the new speaker. Yeah, he did not speak in the earlier sessions. Welcome, IR Lal. Are you around?
Yes.
Okay. And also will be joined by the previous speakers, Professor Datuk Dr. Kamaruzaman, Datuk IR Lim Chow Hock, and also Professor Dr. Dominic Fu. Okay, so in this session, we will try to make a discussion on the topic that is on this water and energy for sustainability. But before that, let me just introduce IR Lal. IR Lal is an electrical engineering graduate from the Brighton College of Technology, United Kingdom, way back in 1963, and served TNB for a total of about 37 years. Wow, that's a long time, IR Lal. He was involved from 1999 until 2010 on national policy development projects on energy efficiency, renewable energy, green technology, and sustainable development, covering green buildings and materials and transport. So this is these topics are very hot nowadays. Yeah, renewable energy, green technology. So IR Lal has been working on it for the last 20 years. So he has been involved in ASM activities since 2008, initially on its alternative energy committee and later as an associate and subsequently as a fellow. So he is now an adjunct professor at UCSI. Okay, so gentlemen, yeah, we would like to start the ball rolling. So we have a very general question. So we will then let each of you to comment. So our first question is, since we're talking about energy and water, so what are the current status and future outlook on water and energy sustainability in Malaysia? Okay, so what are the current status and future outlook on water and energy sustainability in Malaysia? So now we would like to invite first IR Lal, so since he has not spoken, so maybe he can give his perspective on this issue.
Thank you. Good afternoon, good morning, afternoon, everyone. I have not spoken, and I came to invite myself into this panel to be a batu api as far as the discussions are concerned. Now, when I first took on this task, I'd expected my perception on engineering for the tropics was what is the future and direction that engineers must take in terms of sustainability for tropical zones. We have heard that tropical zones have growing population more rapid than the rest of the global community. We also have a possibly greater impact as far as climate change is concerned on the climate, on the weather variability. Now, with growing population, increasing affluence, and increasing demand for utility services, these are going to impose a severe demand on both water and electricity. I have had a lot of discussions with Dato Professor Kamuzaman Sopian and Dato ABJ on OTEC and other issues. But let me just say, first of all, on Dato Lim's presentation on the water, I think the presentation was quite comprehensive, although it was only focused for Malaysia. But I believe all those issues that you mentioned would also apply and can be replicated for other countries in the tropical zones. The one thing that I found that may be missing is a minor issue perhaps, is optimizing water use. He did mention the need to reduce NRW, which can have a big impact on the total water requirements as well as energy use for treatment, pumping, delivery, and so on. So that is one important benefit that is global, universal. The issue is that in Malaysia, we use more water per capita than many other countries, much more than the global average. How can we reduce this? We have our neighbor Singapore, which addressed this issue in efficient water utilization from a few decades ago, and they have succeeded, so Malaysia can succeed as well. I believe engineers can create and develop the systems that are necessary, and engineering should in fact optimize more emphasis on sustainable development. Even myself as an electrical engineer from over half a century ago, we didn't have much concern about the environment. We just do what is required for our engineering purposes. Now, I've grown to realize that environment sustainability is as critical, if not more critical, than the economic development that is going on. So I believe engineers can do that, and engineering education can be nudged towards giving that due consideration. Now, I have, of course, a lot more these points of contention with energy part of it. Dato ABJ has been very passionate promoter of OTEC. I've had a lot of discussions and debates with him over the years, particularly with respect to the timing of the systems, cost, and viability. Because as has been mentioned, OTEC capex is exorbitant, and it is not something that can be implemented on a small scale. It has to go big, and that will go into trillions of US dollars. Dr. Vega, who is basically the father of OTEC, whom I was introduced to by Dato ABJ, has indicated that only when OTEC plants of about 100 megawatts are implemented, which will take up to 20 years after the first 10 megawatt plant originally proposed for Le Martinique Island is implemented, then only it will become more mainstream. And from the reports that you had indicated, even then, the electricity cost of generation would be something like 18 US cents per kilowatt hour, which is not something which can be taken as a viable option among the various alternatives that are available. Now, of course, OTEC produces much more than just electricity. Hydrogen, probably cold water, aquaculture, and agriculture, and other minerals can be extracted from the oceans. So there are alternative byproducts that can improve its net output so that the overall cost per kilowatt hour can be reduced. But even the discussion notes that were given for us for this workshop or this seminar indicated that OTEC is not viable till about 2035. Now, if I take Dr. Vega's 20-year target, if Le Martinique is finally completed in 2020, then it becomes viable more by 2040. And in this respect, again, Dato Professor KS knows very well that the ASM's paper on carbon-free energy by 2050 was under certain conditions where Dato himself, as chairman of the task force, was under no negotiation, no win situation. He had to do something, whether it was practical or otherwise. My own perspective in being involved in renewable energy and energy over the last 2 decades besides my TNV experience, is that carbon-free energy is not possible by 2050 in Malaysia, nor in most other countries, and particularly in the tropics. We know that countries like Germany, Denmark, even UK have on occasions been relying on renewable energy for the whole day's consumption, especially on its weekends and public holidays, when the demand is low. But that does not apply in the tropics. So where do we go from there? In this respect, a lot of talk is on hydro, because among renewable energy, hydro is probably the biggest component at the moment. So rivers that provide hydropower are also sources of water for other use, agriculture, industrial, domestic, and commercial. And there are some really sort of scary examples. For example, the mighty Colorado River, which carved out the Grand Canyon, never reaches the sea because extraction of water along the way for agriculture and other uses exhausts all its water before it can reach its so-called river mouth. In Africa...
Okay, excuse me, Arla. Yeah, do you have any more comments for the speakers? I know you have addressed questions to Datuk Lim, Professor Datuk KS. So how about from Datuk Fu, Dr. Fu? So do you have any questions?
Well, I think Dr. Fu's presentation was above my head. I won't deign to comment on that. But
okay, yeah.
if you have time, I'll stop with that. Thank you.
Yeah, let us take a break for this at the moment, because we want the other speakers also to give their inputs. For example, Datuk Lim, yeah. So could you respond to the comment by IR Lal?
Yes, certainly. I think thank you very much. Dr. Lan has actually mentioned the right point in terms of the aspects of the need under this broad topic of demand management, the need to actually reduce our water consumption, more so in terms of the per capita the consumptions by our populations, and I would say in the tropical regions. Most developing countries, more so in Malaysia. I mentioned in my slide that I think we are probably among the highest, on the average about 210 liter per capita per day. And that also actually varies from state to state, all right? We have the different kind of figures, but certainly I think that figure is too high. I would say that we probably require another separate forum to just look at the ways how actually we can save water, all right? And just to give just a few tips here, I would say that we can reduce it down to very much less, probably to 100 to 120 to 150. Perhaps even can be much lower in Singapore, because we take the abundance of rainfall here and water supply here for granted. Simply because our tariff is very low, people wash cars, 3-4 cars, I don't know, in average of per week, say, and that consumes a lot of so-called potable water. And we're still using the potable water to water the plants and wash the floor. I think that if we can reduce the use of half hours of rainwater to do so, all right. But I think the list can go on. For instance, all right.
During lockdown, they wash more often.
Oh yeah, certainly. And then we tend to bathe 2 times a day, because you feel very warm and humid in tropical humid region. And we're still we tend to sing 2-3 songs of during this. I think that should cut down. All right, limit also probably 3 minutes of bathing and taking bath, and this way I think we can actually save water. Apart from using certain what we call water saving devices, and that I think is easily available today in the market. I think this is what I think we should adopt. Obviously, there's a long list of how we can save water, but I think that would be probably quite a separate forum by itself. But I think it's the way forward that I think we can actually reduce our per capita consumption. I'd like to move on to the other aspect, which I think Dr. Landi mentioned about the so-called prospect of using water for hydropower generation. Certainly, I think we all are aware that there is a strong nexus between the water and energy here, right? And I think the former ministry in charge of water, I think they already come up with a certain kind of so-called policy that come 2025, we're talking about perhaps to look at even to raise the renewable energy to the level of 25%, 20%, and all this 20%, perhaps 50% has to come from hydropower, right? And that's where I think the strongnesses between the water and energy is a concern. The importance of tapping more aspect of water for so-called for energy. But I mentioned also that I think the chances of having building dams in the upstream is very, very slim down today, more so in Malaysia. And I think this is also catching up in many developing countries. People are actually opposing, all right, building a dams in the upper part of catchment. But that doesn't mean we cannot have other sources of other areas of where we can actually tap the water availability, the energy from water along the way, along the whole river system, that we can actually still tap so-called water energy for generations of hydropower. Means probably the mini and the micro, so-called hydropower, smaller kind of generations as well. So certainly, I supported that kind of idea that I think the way forward should be more towards generations of so-called hydropower. Thank you.
Okay. So, Dato', there's one question actually during the chat, during your talk, when you were giving your talk. So the question is asked, how to minimize and reduce the impact of water pollution toward water disruption in Klang Valley. So probably,
I think that is a very interesting topic. And obviously, I think most important is that there are many ways that actually we can in the way control this pollution. First and foremost, I think I would say that I mentioned about the need to change one of our regulations under the Environmental Act, where we're talking about the permissible load that need to be actually discharged into the river. We are using actually a certain kind of a figure, both for the industry as well as the sewerage flows, which I think is not correct. Time has, we need to move on. The rivers flow in the water, amount of water flowing in the rivers varies from day to day or probably from season to season. All right. So the concept of what we call total maximum load is important. In other words, permissible depending on the volume of water in the river for the dilation purpose varies from day to day. So we need to actually come up with, first we change our act, and then finally to instill and impose upon all factories, all right, all factories and perhaps even all kind of manufacturing outlets that is discharged at the effluents, such that they have to control the so-called pollutant at source to the permissible level they can actually discharge into the river, depending on the conditions and volume of the water in the river or the water bodies itself. So I think that a measure that should be the way forward. And I think many countries are even imposing that it's a responsibility on the various so-called industry to even not just having the so-called basic infrastructures of controlling the pollutant source in the factories or outlet. They even have to come up with a so-called monitoring system, online monitoring system, to show to give to the authority concerned that any moment, any time, the amount of discharge is actually in a way monitored and regulated. So I think regulation need to be actually has to be in place first. And the other aspect which I will not probably want to touch so much is I think they need to probably carry out more frequent enforcement. And certainly I think enforcement agency need to be strengthened as well. Thank you.
I think that is more a question of effective enforcement.
Certainly. I agree. Many people ask me these questions. I think in the Asian society, you ask me the first question, I will say it's enforcement. If you ask me the second time, I'll say it's enforcement. The third question is a big capital enforcement again. So I think my slide used a capital letter for enforcement. Thank you.
Yeah. Okay. So that's a very good input, Dato'.
So now we go back to the energy issue. We would like to invite Professor Kamaruzaman to provide a view on this. What are the current status and the future outlook on the energy sustainability in Malaysia?
Okay. Thank you very much, Professor Chong, for session. Okay, I just want to answer back the question concerning the roadmap that we did a couple of years ago. The roadmap was about carbon-free energy. So we include also nuclear option in it. So, but there are two scenarios that we do. So the scenario number one is that this zero fossil fuel consumption in electricity generation in 2050. It means that no use of fossil fuel. And we did that prediction, and of course we give you the results. But I think whether this can be done or not, of course, it requires a lot of investment for that. And there is a second scenario. The second scenario is that the total carbon dioxide emission is basic avoidance from all the carbon resources basically offset the emission from the fossil fuel. That you still use fossil fuel, but it is a mix whereby at the end of the day, the result is net zero carbon dioxide. And then we also we have some in mind that in this particular workshop, in this particular roadmap development, that what about other form of energy? For example, energy doesn't only come in the form of electricity. Energy is in the form of cooling, heating, and so forth. We have that assumption in that. The assumption we make a 10% increase in assumption of energy efficiency. So therefore, all those factors are put together in making the roadmap. I also like to answer the question from Khairul Irawan from Indonesia. Yeah, thank you for joining this. And I think also this question is pertinent. I think also Lal, you can answer this. Which one of the most potential and environmental friendly of tropics energy resource in Asia, among the wind, the wave, the tidal, the geothermal, which of them are the most potential? This is the question asked by Encik Khairul Irawan from Indonesia. My answer to this, and Lal, you can proceed with me after this to answer this. It is a very good question. Because this question asks you which is the best potential. To me, these renewable energy resources, for example, in the tropics, you have all these resources. For example, the ocean, we are surrounded by ocean. You can see offshore wind, you can see tidal, you can also see marine current, and of course, OTEC. Now, all of this energy, they are not in competition with each other. They are complementing each other. The one that decide that is the cost effectiveness. This is cost effectiveness will decide. So therefore, if you ask me the question, what are the best among the wind, the wave, the tidal, the current, and geothermal and hydro? Number one, it depends on the resource. Number two, it depends on the availability, and of course, there is a cost effectiveness to it. There are many software that basically can do the calculation that basically come what is the best mix of it. So it doesn't necessarily that you use solar 100% that you will be cost competitive. There is a mix, and depends on the resources, depend on the demand, depend on the demand of the community for it. So again, to answer your question, which are the best? All of them are the best, but it must be used to complement each other. They are not in competition. Which is Lal, carry on.
Well, I agree with what you said, Dato. The thing is, it's a question of horses for courses. In some places, for example, in Malaysia, we have virtually zero wind and virtually zero wave and marine tidal. But in places like Indonesia, you have tremendous geothermal capacity, a lot of wind and hydropower because rainfalls and mountainous regions. In the Philippines, you have also geothermal and quite a bit of wind and solar PV. Malaysia probably will depend more on solar PV, especially if it's water-based floating solar, as Singapore has actually dedicated to do. Now, if I'm not mistaken, Singapore has declared its intention for floating hydro that even exceeds what we are looking at. For Malaysia, we have the problem of putting solar photovoltaic farms, ground-mounted farms, which actually remove vegetation. So removing vegetation is, of course, removing carbon sink. But the question is, which is the better in terms of the national economy? If removing the carbon sink is worthwhile, then by all means do it. And when we talk of renewable energy being distributed, I think we have to look at it from a slightly different perspective. At one of the workshops in IEM, Dato Badria, who was then TKSU in Qatar, said that criticized SIDA for talking of renewable energy as democratization and distributed, because you have to use vast places for multi-megawatt or tens or even hundreds of megawatt plants, even PV, to get the capacity of energy that you require. Now, people talk of green hydrogen coming from renewable energy. That renewable energy is not enough to supplement or to replace fossil fuels in countries like Malaysia, Indonesia, and Southeast Asian countries. It may be okay in terms of Germany or Denmark, but not here. So we cannot take that as being green hydrogen. At the ASM forum on the hydrogen economy a few years ago, the representative from Lind Industrial Gases mentioned that green hydrogen is less than 10%. In fact, he mentioned less than 5%. At a forum on webinar last month, one of the speakers from Germany mentioned that green hydrogen is actually less than 1% currently. So we have to look at it from that perspective. And hydrogen, even blue hydrogen, is rather expensive. I know Sarawak has 3 fuel cell buses going, and the proposed fuel cell LRT. I happened to speak one of the representatives at IGEN, who are actually advisors to the Sarawak government, and his comment to me was, well, as a pilot project and experimentation is good, even though it may not be cost effective. But on the longer term, on a scaled up situation, it has to be looked at more closely, because fuel cell cycling is not as long for constant use as we would like it. It's excellent for occasional use as standby supply to avoid breakdowns and so on. And hydrogen is expensive. Where you need hydrogen for your industrial process, that cost may not be material because it forms a small part of the total cost. But to produce it for fuel cell, for electricity generation, is a little bit of a different kettle of fish. So we have to look at it in a different way. Have
Okay.
Yeah. Okay, so we know that water and energy are 2 major resources also is a major topics of our today's discussion. So in the perspective of engineering innovation, we would like to ask Professor Fu to give opinion on how to effectively combine these 2 resources into the system design to make the system more effective.
Thanks, Chairperson. In the first place, when we do this separately, let's say some people will do the design of energy recovery system, some people will do water recycling design separately. There are some, even you do it separately, there will be some interaction in between them. For example, if you want to recycle water, you need to use pump. Pump needs to be done, pumps need power in order to operate. So within water footprint reduction, you have carbon footprint as well. And at the same time, the other things also play the same role, because when you recover energy, there will be water footprint within the recovery as well. So if you ask me, I would say we have to look at it in a holistic viewpoint. Okay, so for instance, there are people who say that if I design my system, I replace my fossil fuel with renewable energy, I'm still emitting CO2. Yeah, you are right. Okay, but the whole life cycle tells you that is actually on a net reduction. So what we need to do in Malaysia particularly, we need to encourage more research, okay, especially in the engineering domain, because one thing we know that is that most of the industry do not trust research. Okay, there was one forum that I think one of the organizations did. The industry people say that Malaysian industry is always first to be the second. What is first to be a second? Someone try it before, then only I will follow. Okay, I'm not that brave enough to try it. This mentality is very, very different from the rest of the world. You go to Europe, you go to UK, you go to China, they are there to try the new technology. If no one have tried it, I will try it because I want to get an innovation. And with the innovation, I'll be able to reduce money, CO2 or whatever. But Malaysian industry is very, in a way, skeptical, very conservative. If no one have tried it, no one have proven it, I don't want to be the first white mouse. Okay, I'm scared of failure or wasting money or whatever. They are always the first to be the second. So if you ask me, if we want to have innovation, we can have a lot of innovation in the university, but if this innovation cannot be put in practice, no one try it, Wait until when? Wait until the overseas people try it, then only Malaysian will try it. And this is often the case. Okay. And about 10 years ago, someone asked me, why do you not develop case study in Malaysia? Because Malaysian industry is very difficult to cooperate because they are very worried this, worried that. They don't want to, they're not dare to try it. But the moment you show them the results from overseas, oh, they say, oh, I'm willing to try. So the mentality has to change. Okay, if we want to be innovation, we need to somehow educate more people to let them know that innovation can help them to improve efficiency, improve sustainability, improve profitability. Okay, of course, if you talk to industry, the money still is the main driving force. Okay, you ask that 100 industry out there, maybe only 20 or 30 will say, we are concerned about CO2. The majority will still want to save money. Okay, so you need to tie economic with CO2 reduction or sustainability with them. Then they will find it useful. Right? I think that's my view.
Can I just add on a bit on that?
Ali want to say something?
Can I just add on? Certainly, I think I concur with Professor Dominic Fulton on the need for probably further research. I think first, before that, there should be a national policy, which I did mention that I think time has come for the ministry to come up with national policy, perhaps even mandated in the necessary legislation that certain industry that consume a large volume of water need perhaps to reduce them. And it's a challenge. It's a challenge. Perhaps industries need to do research in terms of how to reduce the water footprint for personal kind of process. Let's say, for instance, the paper and pulp industries, the manufacturing industry, the consumer of water, the glove industry, for that matter, tremendous amount of water is necessary. And if they can come up with research jointly with a kind of mandate that there's actually the ministry side that by a certain year they probably could recycle a certain percentage of water, perhaps even 25%. It was at one time postulated to be 25%. But this has to be in the form of finally in the legislation or some form of so-called conditions in the approval for the factory to run. And this is so then you force the industry to cooperate properly together with the so-called research institutions such as a university to come up with the necessary kind of innovation to reduce the water footprint. And I think that should be the way forward.
Exactly. China implemented a 3-year cycle. Every 3 years, you need to prove that your company will reduce carbon footprint by some percentage.
Certainly. They provide necessary incentive for that. Necessary incentive for the kind of reductions in the water footprint. Right. Thank you.
Okay, Datuk KS, you have experienced this type of interaction with the industry since you are the director for SRI. So what do you think about the inputs from the industry or people or companies who want to actually use up your innovations? You know, what is your experience? Could you share with us?
Okay. My institute deal with solar energy and solar innovation. We have about perhaps 30 over patents in solar thermal and solar even solar cell. So, but we have industrial collaboration. Yes, we do. We have, but not as much as we have with what do you call it, community-based project. We have more community-based project than industrial-based project. For example, if you look at solar cell, as I mentioned in my presentation, there are various what do you call toxic as well as combustible material which is used basically to make those solar cell. For example, the texturing, you use acid, and then you have to wash it using acid. And there are mixture of acid, formula of acid that you use to wash it, for that you have the texture within the wafers with respect to silicon solar cell. And of course, there is also, and these are toxic materials. There are also, we call it, when you make the anti-reflective coating, you will add what is called silane nitride, and this is explosive. If you look at the Bhopal in India before, that explosive material has similar characteristic to the silane. And we have introduced a process whereby it's a dry process, it's used less toxic material, but it doesn't attract the industry. the industry would like to go to the thing that they know that it is like well proven for them, and it's the way business as usual for them. To go into something innovative will require them to invest, will require them to basically, in certain sense, they have to go to the bank, yeah, to get money for it. But even the bank doesn't have that mechanism for. The bank wants something which is workable. It doesn't want something which is. So this is the problem that they face. Yeah. We have also have a lot of solar dryers, for instance, for drying of agricultural produce to get quality products for it. But the industry would prefer either you just open dry. Yeah? Of course, open dry is subject to a lot of things, subject to a lot of quality issues, or you use the ordinary dryer. Yeah, rather than going for an innovative solar dryer. This is well known. Yeah? It's very difficult for industry to go for it. Yeah. At the end of the day, the industry wants to make quick buck. Yeah, and they want to go ahead. Yeah, to use conventional process for it. Yeah? They don't want to wait. Let's say if I tell you that the payback period for a solar dryer is 6 months, they don't want to go for it. They want to go for business as usual. This is the problem. I think this is not predominant in Malaysia only. It's also in other countries. Yeah? They have this problem of going for something new. Yeah? But I think as far as my success is concerned with respect to the solar as my institute, it's actually our more towards the community-based project, more towards a project that deals with social business. Because these are small projects, yeah, and as small is actually profitable. This is the most that the things that I see a lot that we are more successful in rather than the industrial collaboration. Other than that, it's publishing papers. Yeah, it is applying for grants. That is what we are good at. Yeah? And that's about it. Yeah? But I see. The direction is towards that. The direction is towards more environmentally processes, products, and services. So is it the way forward? I mean, they cannot deny this. Yeah? Sooner or later, they have to go to this. Yeah? I give you an example of a handphone. If the handphone is made from a non-environment friendly process or product or something. Yeah, it will not be there for the next 3 or 4 years. Yeah, so the way forward is actually more towards the environment friendly product and services. So it's the way forward. They just cannot deny it anymore. So it will go into that direction.
Yeah. So that's a very interesting comment, Dato'. Regarding what you say is about the community project, that is actually, it takes a lot of your innovation, So what about the funding, for you when you do this community project? Where does the funding come from? Any comments for that?
The funding basically come from organizations, from NGOs, from organizations that would like to perform their CSR, yeah, from banks and so forth. Mm-hmm. Yeah. And I also like to comment one thing, because we are talking about the tropics. Yeah? The tropics is basically, it is abundant of solar energy. You have biomass resources, you have wind, you have so forth. But you have to know that the characteristics of these renewable resources. Yeah. I give you an example of solar. Solar energy, yeah, has 3 components into it. Number one, when you measure solar energy, yeah, the irradiation, you have actually the direct component, the diffuse component, and of course the reflected component. Yeah, and in Malaysia, in the tropics, we are characterized by several. We are characterized by the following. Number one, we have rainy days. We have 170 rainy days, and we only have 3% of the day that we have actually the blue sky. You see, most of the sky are either diffuse or rainy days. If you calculate the total amount of days that we have with blue sky, it's only 3% of the time. So our sky are being characterized by diffuse, very low beam energy and so forth, not blue sky. But therefore, the type of energy device that you need to innovate is basically the device that can cater to this. Yeah, we are, one thing we are lucky. Many people have asked me this question that solar is not, because we are lucky that this 365 days, the rain that we have is in the afternoon. Therefore, we have a nice solar energy between 11, 12, 13, 12, 1 o'clock, 2 o'clock, then we start to rain. Almost 60% of the time is like that in Malaysia. What advantage did it do? Is that the charging time are the free time that we get. The charging time is between 11 to 2. There's no charging time after 3. Yeah. So let there be rain. We don't care. But the one thing good about it is that rain provides a natural cleansing mechanism to your solar collector. Therefore, if you see collector in the arid region, for example, the Middle East, they are full of dust. Dust actually will cut your production by 50% in terms of energy yield of the panel. So therefore, in the energy yield for the tropics, actually, if you consider the long run, is much even better than the one in the Middle East. Yeah, that's why you can see some people who do simulation in the Middle East, when they start to do the real project, they see there is a very sudden reduction in dust. I have a student looking into 30 type of dust to look into what is the effect of the dust. So my point is this, that so does the wind. The wind has certain characterization when it comes to the tropics. So you have to identify that. That's why I said in my earlier statement, there is no such thing, competition between solar, wind, or hydro, whatever. It's actually, at the end of the day, it's the cost of energy per kilowatt that makes sense. Even, let's say you have a PV system, PV hybrid system at the remote areas. It doesn't necessarily is good, because what? The COE will be high. Maybe by charging just a battery and then running the diesel genset is a much lower cost than that. You have to do the calculation. And there are many softwares that can do the calculation. So like Dominic, the Professor Dominic showed here now, there are a lot of ways to calculate and to find basically the most optimum. But in terms of renewable, is the at the end of the day is actually the cost of energy per kilowatt hour, which accounts to. That is my point now, because that's my point that I want to do here, is that you have to know your tropic, and at the end of the day, you have to know what energy that will basically enhance power.
Okay. Wow. So it's very good input, Dato'. That's why this is what the engineering for sustainability is all about. The future belongs to the tropics. Yeah? the whole theme for this seminar is the future belongs to the tropics. Okay, so we are actually almost coming to the end of the session. So a very good discussion among the speakers just now. So before we end, maybe we can have the last words from each speaker. So we start with Dato' Lim first. Any last?
Thank you, Prof. Aisha. Certainly, I think I have been talking about the need to have so-called a good governance in terms of managing our water resources in the country, both in terms of resources as well as water as a utility. And I would like to touch on the important part that while many countries in the tropics like Malaysia, rainfall does now do have the rainfall characteristics that both actually the spatial as well as the temporal, and that's why I think certain time we do experience extreme floods and as well as droughts, you see. And I like to also refer to one of the chat box, which a question in the chat box that talk about how can we actually harvest this flood water, which I did mention also that flood water actually is a resource, you see. It's a resource that actually the $1 million question is how do we actually store this flood water so that at times of drought we can actually use them for our water resources. And I think today the take-home message is that we cannot, or we do not have the luxury having dams at the upstream anymore. They catch only about 10 to 15% of the catchment area. We need to move downstream right up to the river mouth. In short, we are catching 100% of the water of the total catchment within the river basin. And the way forward is the central message, take-home message that I will drive today is we need the concept of what we call the development of coastal reservoir. It can take many forms. Coastal river can take many forms, for which I think for those who are interested, please contact me directly. Certainly, that will be in the next topic for our session. Thank you.
Thank you, Dato'. Yes, Arla, 1 minute comment from you.
Well, I think, as I mentioned earlier, engineering education and practice should go more towards sustainability, and engineers need to be empowered to do what is optimized engineering and not be directed or hampered by governance issues by politicians or others. This is very critical, especially as we have experienced floods, droughts, and water shortages, a lot of it because of poor governance issues at the local level. Thank you.
Okay, so you played your role. Batu api, eh? Arla.
Well, I have to live up to it.
Okay, so yeah, Prof. Dominic, any last words from you?
Okay, I should say Malaysia being in a tropic country, we are actually very fortunate. We have a lot of resources from the traditional fossil fuel to the new alternative renewable energy like biomass or palm oil effluent. We are just blessed, okay? When we are too blessed, people take it for granted, okay? So we need to realize that this is something that we will have to sort of serious about in the next decade or so. Put a lot of political will to do it, and being non-politician or or NGO people like us, we have to sort of give our whatever sort of stress to the politician, push them to move the country to the better way, rather than just relying on some cheap and non-renewable resources. So the sun is always there, 11 to 2 o'clock, every day can generate lots of power for us, and our biomass is always in the palm oil mill or in the wherever you can find it. All these are resources, but we just don't make use of it because we are still producing oil from the ground.
Yeah. We are rich, yeah, with natural resources. Okay, Dato', Professor Dato' KS, any last comments?
I just have one last sentence. Don't let limits you. Go renewable.
Okay,
thank you very much.
Renewable. Okay, Prof. Chong, want to say anything?
I think it's very good to see we have a different opinion from the panel. So actually, I agree with all the panels that we have good resources, and the important is how to make use of it. That's why it's a very good conversation for today's seminar.
All right, so I think with that, I would like to close up the seminar today. It's a very useful discussion, very informative. We have Dato' Arlim, Arla, Professor Dominic Fu, and Professor Dato' Kamarudin Sofian, who have given us, also including Cik Samsul, yeah, he has to give the talk because Dato' Bakar has some urgent matters. Dato' Bakar has to go to, as I understand that Dato' Bakar has to go to hospital. So speedy recovery for Dato' Bakar's wife, yeah, Datin, hopefully Datin will get well soon. And I think we have also got some very good questions from the audience. So thank you so much. Audience, we have about, I think, participants close to 40. Yeah, at one time there was the number also fluctuates, but we got a lot of responses from the audience as well. So thank you very much. Thank you, Dato' Sri. Thank you for initiating this seminar, and so we hope to meet up with all of you again in the future seminar. Okay, thank you. Assalamualaikum.